the whole rationale for designing stacked rapid sand filters is that we wanted to figure out a way so that we could operate a filter without needing to use pumps. And that led us down this path of stacking 6 filters on top of each other and running them in parallel during filtration mode and in series during backwash mode. So that was our little trick of geometry that enables us to use the same flow rate, whether they're in filtration mode or backwash mode, and indeed use the same water, use the water that's coming from the clarifier in both cases. So you just flip the mode between filtration mode and backwash mode. And that's the question, like, how do we do that? Because what a mess. There are 7 pipes that are connected to this filter just for inlets and outlets during filtration mode. And then there's going to need to be yet another pipe that's going to be the way that water leaves during backwash. So that's 8 pipes. And that suggests that, oh, I said 7, and that's right. We need 7 big valves because there's one pipe that is always operating, and that's the bottom inlet to the filter, which part of the time it's providing water to the bottom layer of the filter for filtering, and part of the time it's providing all of the water to the filter to backwash it. So the bottom pipe is always on, so I don't need any valves there, but every other pipe, count them, 1, 2, 3, 4, 5, 6, plus this guy representing where the backwash water goes, 7, would need big valves to turn them on and off, depending on whether you're in filtration mode or backwash. And when we were inventing this filter, I saw that as a showstopper because big valves are expensive. And so if we didn't figure out a way to operate this filter without requiring all those valves, it was going to be expensive and also a pain for the operator to run. So the following slides illustrate how we intend this system to operate. And as Patrick knows, not all filters in real life are actually using our intended design. Some of them, the operators are still effectively using pipes as valves to turn inlets off and on. But the system is designed so that it can be operated with just one single little valve if all goes well. So here's how it's supposed to work. So we'll watch this a couple times before it actually makes sense. This is a cross section of the filter, and I've gotten rid of a lot of the details that I didn't feel like drawing over and over again. So it doesn't include all the inlet and outlet pipes. It doesn't include how the backwash water gets in. It's just the filter box missing all those pipes and showing what's happening to the siphon that is used to either hold the water in the filter during filtration mode or dump the water during backwash mode. So let's go back. This is where we just ended backwash. And we're going to go through the whole cycle so you'll see how this all connects together. And at the end of backwash, we've done something so that this pipe, this siphon here, is full of air. Okay? We did that by opening up this valve and letting it fill with air. Okay? And then that valve is closed and it's full of air. And now we're getting ready to filter because there's no longer any water flowing through this siphon pipe because it's now full of air. So the only place for water to go is either into the filter box or in the filter box and then out the outlet. But the outlet is up much higher, and so it can't get there yet. And so the only thing it can do is raise the water inside the filter box. So all the water that we're adding, remember, there are pipes connected on the inlet pipes connected on the coming down into the sand bed. Those are still there. I just didn't draw them. And so water is entering through those pipes and slowly increasing the water level in the filter. So here it goes again. And look at what happens to the water level in the filter box. And also look at what happens to the water inside the siphon pipe. and see if you can figure out what's controlling the water level inside the siphon pipe. And sorry about the blurry edges. Microsoft thought that the edges should not be clear when you're doing an animation like this. Do you see how the water levels in the siphon pipe moved? Do that one more time. The water levels in the siphon pipe move. Any ideas why? Oof. Or what must be true? I'll guide you through this because there's some really wonderful physics here. Air has a density that's just about negligible compared with water. And so that means if we're tracking pressure changes, the pressure doesn't change in air. Granted, you don't know the pressure does change in air, but not significantly at this scale. So that means that inside this siphon pipe, when we're in air, the pressure is the same everywhere. Got it? And then let's go from one place where we know what a pressure is and into the siphon pipe. So let's start from the top of the filter here. So top of the filter, the pressure is atmospheric. As we go down inside the filter bed, or sorry, inside the filter, inside the water, what happens to my pressure as I lower inside this water? As I go down in the tank, my pressure goes up. Thank you. It goes up. So my pressure down here somewhere is much higher. And okay, it keeps on going higher, and I can then sneak over here. When I travel horizontally, what happens to my pressure in this tank? If I travel horizontally, what happens? Now we draw a line this way, right? No changes. Whenever you're traveling normal to the gravitational vector, there's no pressure change. So that means I can travel across here, no pressure change. And then as I go back up, my pressure increases again until I get to this point. So all that means that the pressure in this air is related to the height difference between this water level and this water level. That's the added pressure in this air. Do you get that? Does that make sense? I can calculate how much excess pressure is in this air based on the difference between this water level and this water level. And now I said that there's only one pressure inside that air column because its density is so low that the pressure is basically the same everywhere. So that must also be true at this end. And you can debate, I guess you can pull out a ruler and see if I drew this correctly, but here's another place where we know what the pressure is. The pressure here is atmospheric. And as we go down in this water column, it increases again by rho g. And so rho gh. And so the difference in water level between here and here must be the same as the difference in water level between here and here. Ooh, was that magic? So that's what causes that water level inside the siphon tube to slowly shift. Okay, and look, this siphon tube is now, because there's air in it, it's able to hold back the water from in the filter box from leaking out. Do you see that? This water in this filter box can't leave via this siphon tube because there's air blocking its path. It's like an airlock. That's what it would be called. It's an airlock preventing water flow. So that's, anybody want to ask a question? I see some puzzled looks, but let's continue on. We'll go through the next one, and then maybe it'll all start making sense as you see how all these cycles fit together. Okay, they go so darn fast. What just happened? Oh my goodness, let's try that again. So now we're going to begin backwash. And so now we're where we were at the end of last slide. And now a couple things happen really fast. So first of all, this operator is going to hit, open up that valve, 15 seconds roughly, and then close it. Wasn't that exciting? You saw absolutely nothing interesting, right? All he did is open up that valve for a little while and then close it. This is what was happening. He opened up this valve. And what do you know about the pressure of this air? Is the air in this pipe, is it greater than atmospheric pressure or less than atmospheric pressure? I see one finger pointed up. It's greater than atmospheric. Remember, when we come in the water and we go down, our pressure increases. And then we can slide across here. And that means that the pressure at this point is greater than the pressure at the top. It's greater than atmospheric pressure. So the pressure everywhere in that air chamber is greater than atmospheric. That means that when we open up this valve, air comes out. And indeed, that's what happens. So let's do it again. Air comes out, and the siphon starts because we got rid of the airlock, and very quickly it drains the water level in the filter. And that was the beginning of the backwash cycle. We even fluidized the sand bed because of this. We've lowered the level in the sandbox, in the filter box, very quickly. And now, because of this, because it's open to the atmosphere here, this is atmospheric pressure, and that prevents it from draining the filter any further. The difference in water level between the filter and this box here would be the head loss in this part of the siphon tube. Okay, otherwise those two levels would be the same. So now, during backwash, this water level is going to stay constant, and we'll get rid of all the dirty water. Okay, that was begin backwash. The next one is going to be end backwash. If we open up the valve now, oh, we have to go through one more step. Thinking about this, what is the pressure in this siphon pipe now? Dun, 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 dun. We have to go back to what we know. What we know is we know that the air pressure here, that this is air pressure right here, or it's atmospheric pressure right here. And so now, as we go down into the filter box, our pressure increases, but as we go up in this siphon pipe, our pressure decreases. So it's way below atmospheric pressure in this siphon pipe, which means that when we open up this valve, air will go in rather than water coming out because it's under a partial vacuum. So let's do it. Let's open up that valve. So we open up that valve and air goes in, and then we close the valve. We caught our air. We caught our airlock. That's going to now prevent water from escaping from the filter when we're in filtration mode. By the way, this is where the myth began that if you animate something in PowerPoint, then it must be true. I'll let you see. I'll let you decide how far you believe that. Just for fun, I was curious, did someone else previously invent this idea and patent it, and so we couldn't use it? Which, by the way, doesn't that kind of upset you? That you could come up with an idea, you think it is original, and then someone else basically read the physics before you got there, and so it's theirs and you can't have it? Anyway, I'll let you ponder that. Happily, the person who invented this invented it a long time ago, and so it's well in the public domain. And it's kind of funny. It was really the big flush inside a toilet. So this was an alternative to the big flapper that is in toilets that are used now, mostly for, at least for in household flushing toilets. So to eliminate that big flapper, they were going to use this little air valve with this same idea. So I guess number 9 is that little air valve, and you were going to reach into the toilet tank and turn that little air valve and let the air out of this air trap, and that was going to start the siphon to do the big flush. And then after it all flushed, goodness, if it flushes all the way down to the bottom, it would actually fill up with air by itself, which is kind of cool. You wouldn't have to reset the valve to fill it up with air. It would just reset automatically by draining the water all the way down to the bottom. That would break the siphon, stop the flush, and you'd be ready to go again for the next time. So the only problem is you'd have to reach inside the toilet tank to initiate the flush. And then there's one other comical problem, and that is that when they designed this, can anybody remember what else should be in this toilet tank that's kind of missing? You've looked inside a toilet tank at least once in your life, right? What else is in there? They're completely missing the valve that adds the water into the tank, the float valve. And they conveniently didn't draw it because it wouldn't have fit. So that's just another minor fabrication issue that they would have had they actually tried to build this thing. I had this suspicion that this got patented and never built, or maybe built one and it's like, oh, this isn't actually that great of an idea. So anyway, now Agua Clara uses this idea because we think